Hello, welcome to this next installment of VisualSim training series. In this video, I'm going to go over VisualSim DMA and AHP blocks. Let's get started with fundamentals of DMA block. DMA receives requests from the request port. If the A task name and A instruction combination is available in the database block, then the transaction will be placed in the DMA channel. If not, then the transaction will be dropped. Based on the A task address, transaction will be placed in DMA channel. One can have multiple DMA channels with user specified channel buffer size. DMA also handles fragmentation, and the fragmented transaction will be placed in the acknowledgement port and will be sent off to the destination through bus. Once the load or store operation is completed, the transaction will arrive at the DIN port. Only after receiving the transaction at DIN port, the next burst or the next transaction in the channels will be sent across to the acknowledgement port to the destination device. If there are no more tasks to be completed, and then the transaction will be sent across to the DOut port to the center itself. Here's a list of parameters that can excuse me, that can be used for configuration of DMA controller. You can specify the DMA channels. It can be tens or 20s or hundreds of DMA channels you can have, and you can specify the channel FIFO buffer size, and you can specify at what speed your DMA is running at, and you can specify the width bytes, things like that. As I said before, DMA controller block works with DMA database block, and it has a table with the task name, the instruction type, and the source, destination, and the task size, and if there are any fragmentation is required, what is the size of the fragmented data, and to which channel you're sending the transaction, and which is your destinations, things like that. If a couple of points on DMA blocks and the channels, the number of, as I said, you can have multiple channels in the DMA block. All these channels operate concurrently, and the incoming request can be fragmented um, into different fragments based on the bus size. All the fragments are queued as a request. As you send the first fragment to the destination device, only after receiving an acknowledgement from that destination device, the DMA block sends the second fragment to the destination. The read command returns as a write signal, and the write returns as a read command. DMA blocks have the delays which are based on the block parameters like the DMA speed and the width size, and apart from this, no additional delays are added in the DMA block. Now let's have a look into a simple DMA example with performing load or store operation. In this case, we have one master device and one slave with an AHP bus as the bus in between. So here we have the master device. As I said, this is the VisualSim environment, and in the right hand side we have the slave device, and all the devices are running at 900 megahertz. At the input side, the task which we have generated from the transaction source is actually by name display task, and the instruction type is of load type instruction. And that means we are reading the data from DRAM using our DMA controller. So as soon as the traffic arrives at the acknowledgement port, sorry, a request port of DMA controller, the DMA controller looks for, goes to the DMA database and checks if it has any uh, task by name display task and the type of instruction it is gonna perform, and if it matches, the transaction will be placed in the internal channels based on the A task address. In this case, we have the A task address set to 1, which means we are sending the transaction to the first channel. The task size is set to 64 bytes, and this DMA block is performing fragmentation, and we are fragmenting the task 64 bytes transaction into two fragments of 32 bytes each. What I'm gonna do is I'm gonna listen to the DMA controller and run simulation. The timing diagram provides you the details about the activities of resources, and the green one at the bottom is actually showing you the DRAM activity, and the middle one is the bus controller signal, and the top one is the bus data, which is having two fragments of 32 bytes each. If you look at the statistics generated for DMA controller, as the first transaction from the transaction source was not meeting the requirements defined in DMA database, so that particular transaction has been rejected. And the next transaction of 64 bytes is fragmented into two parts of 32 bytes each. You can see here the active fragment count is of two fragments, and the first fragment is placed in the acknowledgement port at 2 nanoseconds and is sent across to the destination DRAM through AHV bus. So after performing a read operation on the DRAM block, so it will come back at the D input at 15 nanosecond. This particular delay is a combination of bus delay and DRAM access time delay as well. So only after receiving the input from the DRAM block, so this DMA block sends the second fragment to the acknowledgement port to uh, SDRAM. This is how it works, and if I listen to the input port of DRAM and if I listen to output port of DRAM, I'll be having the details about the access time, how much time it took for performing read or write operation. In this case, we are performing read operation, and the total delay for performing read operation is of 3.3 nanosecond, which is arrived at the input port at 3.10 and which is sent across the output port at 6.40 nanosecond. For read operation, DMA will send the first word um, to the bus, and it will not send, and the remaining words will be delayed internally. Okay. So this is how it works, and as you can see in the AHP block, the bus size is not used, and it will not make any effect on the transaction which is going to the DRAM block. If at all you want to fragment the incoming traffic, once again you will have to go inside the AHP block through performing open instance and specify the AHP mode to false and run the simulation again, and you can see here The first fragment from the from the DMA is actually of 32 bytes and is again fragmented into two parts of 16 bytes each from by the AHP pass. By default, we send uh, the transaction as it is to the output port in AHP block. Let's look into the store operation. I'm gonna change my input transaction to a transaction to a store, and I'm gonna edit this particular thing to store and a command type as write command. Can see here you'll generate the bus control signal and the bus data. Once the bus data is available, that particular data the data is available at the bus, it will be written into the DRAM or at the bottom. This again we are having two fragments of data. For the write operation, DRAM will return the last word and the remaining transaction will be delayed internally. So these are the packet details available at the input port and output port of DRAM. The input arrived at 12 nanoseconds, and for performing write operation took about 9 nanoseconds it took, and is updated as read command back to the DMA, and after 21 nanoseconds it will be delayed by it will be sent across back to the DMA, and the next transaction will arrive at the input port of D input. So this is how DMA controller will work with the DRAM for performing load or store operations. Thanks for watching this video tutorial, and if you have any questions, send us an email at onlinesupport@metablissdesign.com.